Alright, welcome back to Measures of Variability for Ungrouped Data Part 2. This is like some kind of Godfather or Lord of the Rings trilogy. I think it's going to take me 3 videos to get this done. But in this one I want to talk about variance, standard deviation for both samples and populations. I'll talk to you a little bit about the empirical rule and how we deal with non-normal distributions. So let's get going. Alright, I'm going to go ahead and start with the population variance. Remember that the variance for the population is designated by sigma squared. The population variance is simply the sum of the distance that each individual x, remember these are our x's, fall from the mean of the distribution. In this case the mean is 33.04. But because we have these negative values here for those values of x that fall to the left of the mean, remember we can't use the negative values. So unlike the mean absolute deviation where we simply took the absolute value, in this case we're going to use our only other option to remove a negative term, and that's to square it. That's one reason that sometimes the variance is called the sum of the squares. So we're going to determine how far does each x fall from the mean. We're going to take that result, we're going to square it to get rid of the negative values, and then again we are going to divide it by n. In this case capital N, because we're dealing with a population, and populations are represented by the capital N. So let's see what I've done here. Okay, I've got all of my 8 data points that we worked with before, and I've got the mean that we calculated, and I've simply taken 7.87 minus 33.04 to give me negative 25.17. Getting rid of that negative sign in this column, I've simply squared it. 25.17 squared, 633.65. I've done the exact same thing all the way down. I took each individual value of x, I subtracted it from the mean, I got the result, in this case 7.15, I squared it, and that's where I get those numbers in that column. The formula tells us that it is the sum of the squares, because remember we're looking for something that has to do with dispersion, and so this number right here is simply the sum of the squares. Squared all of those values, added them together to get me the 2649.06. Last piece of the puzzle, to divide it by n, the number of observations. Again, I have 8 in this distribution, so I divide it by 8, and I determine that the variance of the population of these 8 drugstores is 331.132, and I'm just going to round it off to 0.13. So there is your first population variance. So how do we get to the standard deviation? That's the simplest thing you're going to do all day. Because the population standard deviation is simply the square root of this variance formula up here. So in order to calculate the standard deviation, once I have the variance, all I'm going to do is now take the square root of 331.132. So, like I said, all I'm going to do is take the square root, 331.132, right here, tells me the population standard deviation is 18.197, which I would round at this point to 18.20 or 18.2. It's all there is to calculating a population variance and standard deviation. What if we treated this data as a sample, right? As a sample instead of a population. All we'd have to do is make one change to our calculation. Because remember, when we use a sample to approximate a value for a population, we have to give up or sacrifice one of our sample size in order to approximate the population. So instead of n in the denominator, I'm going to now have little n minus 1. Okay, so what happened while you were gone, or while I was gone, or while we were both gone? I all of a sudden said, well, what happens if I just treat this information as sample data as opposed to the population? Well, I'm going to change the formula slightly, but only slightly. It's still going to be the sum of x minus the mean squared, but a couple of things have changed. First of all, the notation is now s squared, because remember, for sample data we use Roman letters, and the designation for the mean of a sample is x bar. So every place that I had mu now becomes x bar. Right? And remember, since this is sample data, I lose one of my samples in order to approximate the population. So before, where I had n here equal to 8, I now have n minus 1, which is simply going to be 7. The mean does not change. The mean of a sample and the mean of the population are calculated exactly the same. The sum of the values of x divided by the number of observations in the sample. My x's hasn't changed. My x minus x bar hasn't changed. My x minus x bar squared hasn't changed. This right here is the only thing that has changed about this formula. That I'm going to take the sum of the squares of 264906, and instead of dividing it by 8, I'm going to divide it by n minus 1, 7, and it's going to give me 378.4371 as the value for the sample standard deviation. It's the sample standard deviation. The relationship between the sample standard deviation and the sample variance is exactly the same. Sample standard deviation is simply the square root of the variance. So I take, oh my God, this is the variance. Oh no. I'm simply going to take the square root of the sample variance of 378.4371 to give me the standard deviation of 19.453. So, no different than finding a population variance except for the denominator. No different at all finding the standard deviation from the variance, because the relationship is always the same. The standard deviation is simply the square root of the variance. So, if you can calculate one, you can calculate the other. Just remember that s squared is the variance of the sample, s is the standard deviation of the sample, sigma squared is the variance of the population, sigma is the variance, is the standard deviation of the population. So, now that we know variance and standard deviation, what do we even do with these, and how do we even apply them? That's where the empirical rule shows up. Alright, so how do we apply this whole concept of standard deviation? Remember that if we can presume normal distribution, this beautiful looking bell curve right here, then we know two things. We know that the mean of the data is always going to fall in the center of the curve, and that these two halves of the curve are equal, because the characteristic of the normal distribution is that it is symmetrical about the mean. In other words, if I folded this curve right down in the middle, this half over here and this half over here would be mirror images. Because we know that, and because we presume normal distribution, then we can begin making some assumptions about where the data in our distribution falls relative to the mean. The first thing that we know is that plus 1 standard deviation from the mean and minus 1 standard deviation from the mean in this area right here, plus or minus 1 standard deviation of the mean, will always fall 68% of my data every single time, provided we have normal distribution. So what happens when I move out 1 more standard deviation? So now if I go plus or minus 2 standard deviations from the mean, right? 2 standard deviations from the mean, what I end up capturing here is 95% of my data every single time. This was plus 1, this is plus 2, this one was minus 1, this one is minus 2. What happens if I go even 1 more out? So now I'm going out plus or minus 3 standard deviations from the mean. This side is plus 3 standard deviations. This side from the mean here is minus 3 standard deviations. And I know that once I go plus or minus these 3 standard deviations from the mean, every single time I will have 99.7% of my data. Because the curve is normally distributed and we presume the mean to be in the dead center, we consider this to be the positive or the upper side of the curve. We consider this to be the negative or the negative side of the curve. It has nothing to do with the values along this horizontal axis. What it has to do with is, how am I moving up and down the curve relative to the mean? Well, I'm going above the mean, which means positive. I'm going below the mean, it means negative. So when I go above the mean, I'm going to add the value of the standard deviation. When I go below the mean, I'm going to subtract the value of the standard deviation. And this 68, 95, and 99.7% rule will hold true for every single curve, every single distribution you ever see, provided we assume, make the assumption, that it's normally distributed. So that's a normal distribution, which is nice. But what if my curve looks like this junk down here? I can't presume normal distribution. It's all lumpy and bumpy, but I still want to make some determination as to how much data falls plus or minus any given or suspected value from the mean, expressed in standard deviations. These being above the mean and these being below the mean. Based on that is when we apply our Chebyshev's theorem. This is where we apply this theorem of 1 minus 1 over k squared, where k represents the number of standard deviations. So if I want to know how much data falls plus or minus k, or say in this case 2 standard deviations from the mean, which will be somewhere here and here. So we'll say this is plus 2 standard deviations, this is minus 2 standard deviations, oops, plus 2. And I obviously have a goofy looking curve here that's not normal. If I want to know what percentage falls in between this value and this value, I simply substitute 2 for k, and then I solve. So what I've ended up doing is, we said we wanted to know how much data fell plus 2 standard deviations from the mean and minus 2 standard deviations from the mean in a non-normal distribution. Applying the theorem, I say k is equal to 2. I plug in for the formula. 1 minus 0.25 is 75%. And now I know that for a non-normal distribution, plus or minus 2 standard deviations from the mean will identify 75% of my data. So that's really kind of a brief overview of the second set of measures of variability. And when I come back, I'm going to talk to you a little bit about z-scores and coefficients of variation, and you guys will be done.